Okay, this is lecture 15, PDEs, part B. What we'll be discovering in this part of the lecture, or the second part of the lecture, is how to determine a Green's function on a rectangle. Okay, the approach is very similar to that of the circle. Once again, you have your domain, which is now a rectangle in which you're interested in what the Green's function is. You have your field point P and your source point Q. And just to formulate it formally, let me write the rest of the stuff down. So the aim is to solve the Laplace equation on U is equals to a source given on a rectangle, which is this blue square, bounded by x equals to 0, x equals to a, y equals to 0, y equals to b. And just for simplicity, we're going to assume that you have Dirichlet boundary conditions. That is, the function is specified on the boundary C, which is this blue curve around the outside. Okay, so what we're going to do now is to try and determine the Green's function that would make writing down the solution in general, even though you don't know what G and F is, possible. So if you remember, our Green's function equation is just the Laplace of G is equals to the delta function of R1. In other words, this vector that joins your source and field point. And that delta function is 0 only if R1 is 0. In other words, if Q corresponds to P. Another way of writing that down is simply writing it not as a vector delta function or a delta function of a vector, but rather as the product of two delta functions. In other words, which expresses exactly the same thing. If x prime is equals to x and y prime is equals to y, only then is this Laplace of G non-zero. For the rest of the domain, it's completely zero. Okay, and we want to solve that given the Dirichlet boundary conditions, and to get the Green's function for Dirichlet boundary conditions, we have to set G equals to 0 both on x prime equals to 0 and x prime equals to a. And when your source point is on this line or that line, in other words, y prime equals to 0 or y prime equals to b. Okay. And what I'm going to do now is introduce a new method of doing so. In the previous, we found the symmetrical solution, then we added a function. This method makes use of a Fourier series technique. So this technique you can basically use if your equation is separable, right? In other words, and we'll see that it's separable. We'll see why now. But there are very special coordinate systems, one of which being Cartesian, in which this technique works really, really well. Okay, so before we start the technique, let's just simply say, observe this thing. Note that sine of n pi x prime over a is equals to 0 on our boundary condition, on our boundary conditions in x. In other words, a set of basis functions where if we evaluate this function at x equals to 0 at 0, as well as at x prime equals to a. Okay, and this is useful because it allows us to set up or construct a Green's function that automatically satisfy at least these two parts of the boundary conditions. So before I write down the general Green's function or the general approach to the Green's function, let's look at a number of identities that occur if we multiply this above equation for the Green's function by sine of n pi x prime and then integrate over dx prime. Okay, so we're basically integrating for a given y prime, we're integrating along this line at the bottom. Okay, so the first thing, if we integrate this side of the equation, the left-hand side, we basically we can write out our Laplace operator explicitly in Cartesian coordinates. We multiply it by sine of n pi x prime over a dA. Okay, and then that is equals to the right-hand side. Okay, and if we do that, we can get this identity. Because the integral is only over dx prime, we can take out the delta function of y prime minus y. and we're left with this expression. And if you recall, the delta function convolved with any other function is simply the function evaluated at the point at which the argument of the delta function is 0, provided, of course, that your x lies between 0 and a. Okay, so this right-hand side then evaluates to the delta function of y prime minus y multiplied by sine n by x, right? In other words, it becomes the sine not at x prime, which is related to your source point, but the sine of the function at x itself, at the field point. Now we're going to go back and we're going to look at this expression. We're going to look again at the left-hand side. And the first thing we're going to do is take this first term and try and simplify it somewhat by integrating by parts twice. Okay, so what we're now going to do is basically take this gxx sine n pi x over a, and integrate by parts. So to express that, what I've basically done is I've taken this gxx sine n pi x over a and rewritten it as a part that I can differentiate minus this other part g sine n pi x prime over a. Okay, and you can do it systematically. First take out the first derivative, do a formal integration by parts, or you can simply check that if you differentiate this beast and subtract this term in g sine n pi x, then you basically recover our original expression over there. Okay. The thing to note here is if you write it in this way, when you integrate it from 0 to a over dx prime, this thing here is a boundary term, and you only have to evaluate it at x prime is equal to 0 and x prime is equals to a. And when you do that, sine is 0 at both those points, and g, by construction, is also 0 at those 2 points. So this term vanishes, and what you're left with is the integral of this thing over here. So n squared pi squared over a squared times g sine of n pi x prime over a. Okay, and what is further nice about this is you've effectively replaced your derivative with respect, your second derivative with respect to x prime of g with a constant factor. Okay, which will be convenient in the rest of the derivation. Okay, so now we can go back and express this equation here, which is effectively the left-hand side of our Green's differential equation, as follows. Okay, which is something we'll use again in time. So we've lost the we've basically integrated or taken in some sense this Green's function over x prime, so we've integrated along that line, and the Green's equation then becomes this differential operator in y minus a constant applied to this expression over here, and it's equals to the left-hand side, which is simply this. Okay, so the next step is to let g be equals to an expansion. Okay, and this is what I meant by this type of thing is valid in any function where you can like separate out the parts of the solution. So we're going to say g is equals to an expansion over sine m pi x prime over a times some function of y prime, and we sum it from m is equals to infinity. So if you've ever done any work in Fourier series or ever, you'll know that you can always do this and that it's a complete basis, provided g is sufficiently smooth. Okay, and in this case it is. So let's now let g equals to that, and what I'm going to do next is basically use this identity that sine of n pi x prime over a sine of n pi x prime over a is orthogonal, or the sine basically makes a series of orthogonal basis functions. Okay, and that's expressed that this integral is non-vanishing only if n is equals to m. Okay, and if n is equals to m, you're basically taking the integral of sine squared n pi x over a, and that's always equals to a over 2. Okay. If m and n are not equal, then this integral vanishes, and a quick way to see that is simply that you then have an oscillating function that is 0 on the boundary, so on average the oscillations above and below the line are equal and cancel each other out, and you have 0. Okay, so that's the orthogonality relation for the basis functions. And we can use this orthogonality function basically to find an explicit expression for ym of y prime. And the way we do that is simply to take the integral from 0 to a of g times sine n pi x prime dx. And the moment we do that, we basically rewrite this integral as, we have a factor in front here, 2 over a, times, we substitute g into this expression. So here's your whole g expression. And then you basically use your orthogonality relationship over here. So this thing is non-zero only if m is equals to n, if you've taken this thing out of the integration sign. And that you can always do provided the series converges. And we have that simply equals to yn of y prime. So we found an explicit expression for the sort of coefficients of sine that we've put into this expression for our Green's function. And what is even more valuable is that we actually have found an explicit expression for the factor that we got in this purple equation. If you look at this purple equation that was derived from our full two-dimensional Green's function by integrating over the sort of in the x direction, is that this expression that we have here is exactly the coefficient yn of y squared down here. Okay, so we now have our Green's function expressed in terms of this coefficient, okay, in general, and we also have a differential equation for this coefficient over here, and the next step requires simply solving explicitly for these functions yn of y prime. Okay, so this just summarizes what we've done so far. We've expressed g as a sum of two functions of the different variables y prime and x prime, and we have found yn of y prime as an integral of g multiplied by sine n pi x prime dx prime, and we know that yn y prime obeys this differential equation. Okay, and we're now going to go about integrating that differential equation in a way that's analogous to the way we found the symmetrical solution. If you recall, this thing is strictly speaking a density, so it's not a function itself, and it only makes sense under an integral sign. So what we're going to do is we're going to again integrate this equation above here once. Okay, and that gives us basically this first term. If we integrate it once, it just becomes the boundary condition. So it is dy n dy prime evaluated. We're integrating from 0 to some y bar. So it's basically evaluated at 0 and y bar minus n squared pi squared over a squared times the integral from 0 to y bar of yn prime dy. Yn y prime dy prime. And then this integral over here is simply 2 of a sine n pi x over a multiplied by the integral over the delta function. And this last term here reduces to the Heaviside step function. And just to note, it's not heavy as in having a lot of weight. This is actually the surname of a guy who used it the first time. And it's spelled that way. Okay, so just to recap, that this integral from 0 to y bar of delta y prime minus y dy prime is equals to 1, provided y is less than y bar. Okay, so if you have the fact that this thing has its spike before y bar, if this thing becomes, if this thing in here has a 0 point in the domain of integration, it is 1. If this part in here has no 0 point, in other words, if y bar is less than y, which is less than b, then the value is 0. Okay, and this is basically can be rewritten as your Heaviside step function of y bar minus y, where your Heaviside step function is 1 if this thing is greater than 0, and 0 if this thing is less than 0. Right. And we can then write out what yn derivative at this number y bar is, and it just comes directly from here where I've moved the minus y in derivative value of 0 to the right hand side. I've also moved this function to the right hand side, so there it is, plus sine n pi x over a, the Heaviside step function of y bar minus y. Okay. And now we can do several things of it, and the most valuable thing is to actually try and explore the function y's behavior when y bar gets close to y, right? And the reason we do that is that that's where this delta function becomes important, or non-zero basically. So all the interesting things happens when q starts coinciding with p. Okay, so to explore that, let's let epsilon be greater than 0, and let us simply evaluate this function at y plus epsilon. Okay, and if we do that, we then get, just writing out this thing at y plus epsilon, the only place where it changes is this bound of integration, becomes y plus epsilon, and this Heaviside function we can evaluate, and it simply equals to 1 because y plus epsilon minus y is just epsilon, which is greater than 0, which means it's 1. Similarly, we can now also evaluate the same thing at y minus epsilon, and these two terms are the same except that our integration bound has changed over there, and this Heaviside function evaluates to 0 because y minus epsilon minus y is minus epsilon, which is less than 0, which is basically means it vanishes. Okay, and we're interested mainly in the jumps of the function as it traverses the y value of y prime equals to y. So if we take the difference between these two expressions, this y prime of n, y prime at 0 vanishes, and we're left with this difference. Okay. And also note that here I've taken this domain of integration where I have the y prime n of y plus epsilon, this term entering here. Okay, is the integral from 0 to y plus epsilon, and I've subtracted the integral from y minus epsilon, so I can just rewrite it there. So it becomes an integral over a very limited domain centered around the field point as y value. Okay, and then you have the sine 2 over a sine n by x term coming in over there. The next thing we can do, if we can integrate once more, okay, and by integrate I mean we can integrate this expression for y prime n of y bar from basically y minus epsilon to y plus epsilon. And if we do that, note that this is just an integral from minus epsilon to epsilon of a constant. So that's 2 epsilon right, that's 2 epsilon y bar n of 0. And then here I've just added this integral in front of this yn y bar y prime dy prime dy bar. Okay, and then this final term is the integral of the Heaviside step function from y minus epsilon to y plus epsilon. Okay, but remember that Heaviside step function is just 1 if it is greater than 0. So in fact and that's only true for half of epsilon. I mean for basically y plus epsilon greater than y. So that basically becomes epsilon times that region, and we're left, so we basically have this, that the integral from y minus epsilon to y plus epsilon of the Heaviside step function is simply epsilon. Okay, which allows us to further simplify this expression. Okay, and just one more comment that I sort of skipped at the beginning. This integral from y minus epsilon to y plus epsilon of y derivative or big Y derivative, you can simply express in terms of the boundary conditions, and this is why we completed the whole exercise, is because it gives us an indication of the jump of Y on the left and the right side of the field point. Okay, and what we're going to do now to get the exact behavior at the field point of the Green's function is to take the limit as epsilon goes to 0. And when we do that, we simply have that this term vanishes, it's 0. This term over here also vanishes because we're now integrating as epsilon goes to 0, we basically integral from y to y is 0. Okay, and this final term over here is basically equals to epsilon because of that factor times this term. So that also goes to 0. So we effectively have, if the limit as epsilon goes to 0, that y on the left and y on the right is the same. The difference between the two places. So the y is continuous over the point y prime equals to y. This, however, is not true if we look at the difference in the derivative, right? Over here, if we take epsilon is equals to 0, this integral goes to 0 because it's just the integral over a point which is by definition 0, but you're left with a residual term that is not 0. Okay. Right. So basically, as I've said, the limit of epsilon goes to 0 allows us to fix the conditions of the continuity of the function in our expansion yn of y prime and its derivative yn prime of y prime as y prime is equal to 0. And just to summarize what I've already said, we call the limit from the left basically what happens at y minus, and the limit from the right basically what happens at y plus. And then we have this expression that y, our expansion function to the right minus expansion to the function to the left is equals to 0. In other words, the function is continuous. And the derivative of the function to the right minus the derivative of the function to the left has a jump in it, so it's not continuous. So it basically is, it doesn't have a smooth derivative, so it basically can have a kink in it. Which we'll see is something, we'll actually compute the kink explicitly. Okay. Now, so we basically understand the behavior if y prime is equals to y. So when our source point approaches our field point, what we need to do is to get the full solution is to explore what happens when y prime is not equals to y. In other words, when our delta function, when our function yn simply obeys an expression, this expression. Okay, which we derived on the first slide. And when it obeys this differential equation, you can write down the general solution for yn of y prime, okay, and a general solution of your first order, of a second order ODE is simply as two independent functions, and in this case, e to the alpha y prime, where alpha is equals to n pi of a, and e to the minus alpha y prime, where alpha is equals to n pi of a, are the two independent solutions. Okay, so we can write our function down like that, but now we don't want the general function. We want the function that obeys not only the boundary conditions, but also these conditions of continuity at y prime equals to y in the function, but possibly with a discontinuity with a discontinuity in the functional derivative. So we're going to now look for that specific solution. Okay, so let's see how we do it. So we have our general solution. We have boundary conditions that yn is equals to 0 if y prime is equals to 0 and y prime is equals to b. So the first thing is, let's evaluate what happens if y prime is equals to 0, and then you can write down conditions on C1 and C2. And if you do that, you basically have that if y prime is equals to 0, then C1 e to the n pi over a must be plus C2 minus n pi over a, okay, times 0. So it's basically C1 plus C2 must be equals to 0. And so C1 is equals to minus C2. So yn is simply the sinh of y prime n pi over a, okay, times some constant that we don't know. Okay, so you've lost, by making the y prime equals to 0, you've lost one of these functions. Similarly, if you require that y is equal to 0 at y prime equals to b, you can also solve for one of these two functions, and you can express the solution that has this property as follows. Okay, so here's the first case. If y prime is greater than y, in other words, up here, okay, you basically have that your y prime minus b, you can express it this way. In other words, you can have that when y prime is equals to b, this function is 0, so you satisfy your boundary conditions, multiplied by some constant, and you can have this one where d2 of sinh of n pi y prime over a is equals to 0 when y prime is equals to 0, in other words, basically down here. Okay, so this solution basically works in this part, the part above the red line, and this solution holds in the part below the red line, and it satisfies the differential equation as well as the boundary conditions. Okay. And what remains now for us is to fix these constants d1 and d2, and the way we do that is to require what we know about yn when y prime is equals to 1, or is equals to y. In other words, when y prime is on this red line. And those are these conditions on continuity and the jump in the derivative that we've just derived. So we use those to fix d1 and d2. And what we'd basically say is that y prime equals to y, your function is equals to d, okay, and it's continuous. Therefore, d1 divided d1 multiplied by this thing is simply equals to d. And then we can basically write down d1 as d over the sinh of this thing where y prime is now equals to y. And similarly, we can write down d2 is equals to d divided by this function where y prime is equals to y. Okay, so there's the first case. There's the second case. So what we've done by imposing this condition of continuity in the function is simply to decrease the sort of unknown constants in our equation by 1, by expressing both d1 and d2 as in terms of d, the value of the function of y evaluated at y prime equals to y. Okay, and we can go one step further because we have to require that the derivative of y at y prime obeys basically that jump, and the way we do that is simply to take the derivative of this yn over here. So the derivative of sinh is cosh, we've got to basically make sure that the difference between the derivative on this side of y prime greater than y and y prime less than y is simply 2 over a sine n pi x over a. Okay, so here I write out the difference of the derivatives. So it's basically, here you have cosh of the argument multiplied by the derivative with respect to y, which I've taken out. And you have d2 of cosh of the derivative of that bottom one, where I've taken n pi over a out. Okay. Then I substitute what I've derived for d1 and d2 to be in terms of d. Okay, so there we go. So then I basically have d times something that does not depend on my source point, but only on the field point. Okay, and I know the size of that jump has got to be 2 over a sine n pi x over a. Okay, so I have that. And I can then solve for d. Okay, and I can substitute that d into this definition of d1 and d2, and that d1 and d2 I can then substitute in there, and I have a closed form expression for yn that enters into the expansion. Okay. Okay, so our yn is explicitly known with no free functions. And then as a result, the Green's function also is explicitly known. So we have yn y prime of sine n pi x prime over a. Okay. And these yns are ugly, but they're easy to write down and they're easy to program into a computer. And I guess the one thing that you could ask is that earlier there was a theorem that for the Green's function, if you exchange, there was a symmetry. In other words, if you exchange x and x prime and y prime, you should have the same function. And here it doesn't seem immediately obvious, but the fact is it actually is. The symmetry exists in this function. And just to see the x part, you should maybe see that the d, which basically multiplies yn, is proportional to psi n pi x. Okay, so you basically have sine n pi x prime times sine n pi x over here. So it's symmetrical if you change x and x prime. And a similar thing is true, but it's just slightly more complicated if you look at y prime. Okay, and you were to multiply it out in terms of the exponents. In other words, if you were to take this complicated expression for y that enters into the coefficient over here, and you were to multiply the whole thing out, you would actually see that it's symmetrical if you switch y and y prime. And I encourage you to actually do that. Okay. So anyway, so this basically concludes the lecture. We've now explicitly found this Green's function. As I've mentioned earlier, methods for finding Green's functions, a lot of people have collected them over the ages. They're dependent on the boundary, so there isn't a one-stop method all the way through, but you sort of get used to them and you start collecting them for specific boundary conditions, and they become exceedingly useful if you have to solve a problem on a certain domain in which the Green's function is known. So this is just illustrating another technique of how to do it for the case of a box. In other words, expanding it in terms of the sign basis functions and then reducing the second order equation to a or the second order PDE to an ODE, which you can then solve in one of the dimensions. I should also mention that exactly the same method is possible if you have a domain in which you basically shift this boundary in y equals to b out into infinity, and this boundary here at the bottom also out into infinity. In other words, if you have a strip of x greater than 0, less than a, and y unbounded, okay, then you can actually use exactly the same method, except that here, when it comes to finding the general solution, it becomes actually easier to do. And I possibly would leave that as an exercise for you to do in time. Okay, that's all for me for now. Thank you very much.